heterogeneity of the systems, or how much information, or how many bits are encoded in bits of information encoded in a symbol. So once again, I think this is a formal definition, right? So basically, the entropy is the sum over all symbols. So I have to stress that, right? That there is, you cannot calculate entropy just over single symbol. Entropy we can speak about entropy only when we deal with a full alphabet, where each symbol is described by a certain probability P. And of course, the sum of all probabilities within the alphabet equals 0, right? So we need to have like a complete set of symbols that can occur. And the definition is just the sum of the probability of, the sum over all symbols in an alphabet of the multiplication of the probability times logarithm base 2 of, either the 1 over the probability, or as you can see, hopefully in this case, here we have the probability, but we have also the minus sign at the front of the entropy. And in the lower instance, actually, you can see that it's just a logarithm base 2. So it should be clear that they are interchangeable, right? So okay. What's actually also quite important that typically this logarithm base 2, this is actually it's actually introduced. This is the thing which actually allows us that if we have double the amount of bits, it actually means that we have double the information content, right? So basically, this logarithm base 2, that's where nowadays, even in computer science, where you see that bits, that we can speak about bytes. That was like the origin of this notation. Anyway, sorry. Okay. So and then again, just to get how the entropy works. So again, we have this reminder of the coin flip, right? So we have a coin which can land on head or tails, and basically we bias our coin over here, right? So we say that the probability pk, in a fair toss, this is half-half, but of course, we assume it doesn't have to be like that. However, from even the simple case of the entropy, you can see that the entropy is always maximum when the probabilities of each event are equal, which intuitively should make sense, right? Because then every symbol, every occurrence is equally probable. So, we have pretty much, we can do a guess, right? Or go to a bookies. You don't really get, any insight into your system. That's why the entropy is the highest and the system is most unexpected, so to say. Whereas once you decrease the probability, so one option is more probable than the other, your entropy decreases, right? Simply because you can say a little bit more in the stochastic sense about your system. And as a matter of fact, it doesn't really matter whether you, whether the heads are more probable or tails are more probable, or zeros or ones. It doesn't matter, right? Because it's the probabilities need to sum to 1. So it doesn't matter which way you go. That will cause your entropy to draw. And the important lesson for telecommunication systems here is that you could actually include this information into your coding, into your system, just to be a little bit more efficient, a little bit smarter on how you communicate or how you transmit the data. And we'll actually see example of that later on today, of how we can actually compress, as you may say, the data using this principle. Right. Then we talk a little bit about digital systems and Nyquist-Shannon sampling theorem. This is something it's really should be in the always on the back of your head. So if you are sampling any time domain signal, you should always ask yourself a question: what is the highest frequency of that signal, of the spectrum of that signal? And then if you want to do sampling or discretization over time, you always need to use the double the maximum frequency of that signal. Otherwise, you may be losing some information and you may not be able to recover back your original signal. And then since we speak about sampling, that's sampling is discretization over time, but for digital systems, we also need some quantization over amplitude levels, right? And over here, we're just simply mapping continuous input in discrete output. And what's important, contrary to the sampling in time domain, over here, there is basically no equivalent of the Shannon-Nyquist criteria. So we always lose some information, right? And this is called quantization error, and this is the portion that you see over here. Okay, and then we talked about pulse code modulation, which this is one of the most basic ideas of if you want to digitize and transmit some any analog signal, well, what you should do? Well, you have a source, then you apply the low pass filter, which, as we discussed earlier on, this is to avoid aliasing. It is sometimes actually called anti-aliasing filter because of that. Then we do the sampling using the Nyquist criteria. So in that case, right, it's the bandwidth of 4,000 or 4 kilohertz. The sampling frequency should be at least 8 kilohertz. Then we do quantization. So we assume, due to some requirements, that went 256 discrete amplitude values, which translates simply to the 8 bits, right? 2 to the power 8 equals 256. And then simply, if we want to assess how many bits per second we need to transmit that signal, it's really simple. We got 8,000 samples from the sampling criteria per second, right? Times 8 bits for each sample, so that gives us 64 kilobits per second, right? And lastly, so this gives us information of how many bits per second we require or will be generated by the signal we are transmitting. And then also on the other side, we want to see what is the capacity of our channel that we are using. So basically, whether typically we want our channel to be greater than the amounts of bits per second that our communication will generate. And this can be calculated using Shannon heart rate theorem, right? So what's important here, we see the bandwidth W, again, logarithm base 2 of the signal to noise ratio. That's something you should be familiar, plus 1, right? And this overall will give us the channel capacity. And then what we do, we compare simply our channel capacity with the bits. And if we generate less bits per second than our channel capacity, well, then actually good news. It means we can transmit over that channel with arbitrarily small error or with as little error as we can, assuming with appropriate coding. But that's we'll talk about a little bit later on. Okay. And then speaking of coding, this is just a general categorization of channel code. Two most important I would like you to know are block codes and convolutional codes. So basically, block codes, you have a stream of bits which is chopped into a block, and then each block is appended with a certain number of additional bits to compensate again the noise. Well, sorry, not to compensate, to allow either error detection or error correction in the presence of noise in the channel. Whereas convolutional code, as the name suggests, it constantly performs a convolution operation. So it's a bit like, it doesn't chop your stream, it just constantly operates on a rolling basis on your bits. So far, again, any questions? Is everything clear? Okay, so great. So now I wanted to move on to just some more practical example of what we talked on the last lectures. So, let's imagine yourselves that you're in a, it's actually an example which my colleague, Dr. Borowitz, came some time ago, but it seems to be quite nice. So let's imagine ourselves that we are in the village of Native Americans, right? And well, there's this village over here, and there is a scout, or well, basically some guy. Sorry, right? Sitting on the watch somewhere on the mountain, right? And basically, we are expecting some guests for Thanksgiving or whatever. So basically, we agreed with the guy, sitting the watch, that if he makes a single flash, he will simply signal the arrival of our guests with a single flash. Whereas if there's no flash, the guests are not coming, right? And this seems quite simple, quite intuitive, right? However, there are like a few problems with that. So first of all, as you see drawn here, we have a sun, which may cause some reflection, right? So at the end of the day, we see a flash, and we cannot be certain really whether it's really the signal that they are coming or just some noise, coming from the flickering of the sun. Now, the most simple thing our Native American friends can do here, what do you think? I mean, so how they can basically change the coding to avoid this, to have at least some error detection first. Anybody?
Maybe let's mean like 2 or more signals in quick succession.
Mm-hmm. Yeah, exactly, right? So yeah, this is what we talked over the last lectures, basically, right? So basically, we can agree that 2 flashes means they are coming. We still keep, for the time being, no flashes or 2 consecutive 0, let's say, as they are not coming. And then basically our symbols, so 1 0 and 0 1, so where 1 denotes the flash, they are kind of out of dictionary, right? So basically, with that, if we got a single flash, it means there was an error on the transmission, right? And this is better than the previous case. However, what I hope this illustrates is that, okay, with a single flash, we know that there was an error, that there was a mistake. However, we are not really sure whether this is just, 0 0 with flipped single bits due to sun reflection, or are they actually really coming and we just missed the second flash, right? Because I know of dirty lens or whatever happens. So this is an example of error detection, but still we know there is an error, but we don't know what the correct answer is. And of course, we can stretch that coding a little bit further, right? So we have 3 flashes for they are coming. They are not coming is our 3 zeros, right? And all other combinations are out of dictionary, right? And then with this, we can hope to see that in this case, we have not only error detection, but error correction, right? Because if we get within a sequence of 3 bits, let's say 0 1 0, right? Well, in general, the probability of a single bit flip is greater than the probability of 2 bits flip, right? So in general case, we can assume actually that most likely operating here with probability. So most likely, if we get sequence like 101, it is more likely that it's a triple ones with a single bit. Sorry. Or here, right? Sorry, for the same. So it is more probable that it is the triple ones, which means they are coming with a single bit flip, than the message triple zeros with 2 bits flipped. All right. So bear in mind here that this is, of course, error correction, but it still operates with certain probabilities, right? So even though a double bit flip can occur is less likely than a single bit flip, it can still happen, right? And from probability course, you should know that it's just the right of the large numbers. So if you transmit really huge amounts of bits, you know, even if the double bit flip is less likely, even with the small probability, it will happen eventually if you get infinitely long set of messages, right? So you have to be careful here that even though we have we can embed error correction and we can, you know, correct our errors, it's still not perfect, right? So we always, when designing the code, you always have to ask, where is the stop criteria? I mean, what type of errors are the most probable? Because you cannot guard your system for every single type of error. I mean, you know, you always have to design and think, okay, that's the most probable, and I will secure my coding with these features. But you know, it's never going to work 100% because that's the nature of stochastic processes. All right. Now, the other issue here, which also should be clear, that right now you're actually transmitting single bit. Sorry, you're using like a bits of symbols or free symbols for, you know, information that should have entropy of at least 1, right? Because, you know, either they are coming or they are not coming. So over here, your information is just a single bit, right? Because, you know, there are 2 possibilities. Depending on the probability, you might get actually even less than 1, but we'll move on to that later on. So at the end of the day, you have a redundancy of, you know, 2 bits. So you use triple the number of bits that it's worth it, really, right? So again, you don't want to extend that too far to combat more types of errors. So what's actually the solution? Another one. Well, we can be a little bit smarter here and, you know, use the entropy concept that we learned on the last lecture. And we can say, like, okay, if you are, you know, expecting guests, right? You're cooking dinner and or even organizing a bigger party, you know, within certain time slots, you know, usually most of the times the guests are not coming, right? I mean, you have like a in the sense that, you know, if you are waiting for one single guest and let's say you're sampling every minute, well, in the 10 minutes, there will be only one guest, right? So most of the time, really, nobody is coming, right? And that's the rare event that somebody is coming. So what you can do with that? Where here comes very helpful something that is called variable length code. All right. So what we do? Well, there's nothing that says the 2 message, they are coming and they're not coming, need to be encoded with the code of the same, with the code words of the same length. So what we do? Well, if they are coming, we assign simple triple ones, and every single zero would be simply, they are not coming. This is an important question you should ask yourself here. I mean, what is the probability that they are coming? Okay, and coming back to the entropy and coming back to this, Bernoulli curve. Okay, so basically, if we have maximum entropy, so if every symbol is every event is equally probable, there's pretty much no useful for varying length code, because every symbol is equally probable, so there's no point making any distinction between them, right? However, if we move towards sides of the curve, so for example, sorry, but if we are moving towards the sides of the curve, so one event is more certain than the other, well, what we can do, of course, if they're not coming, it's much more probable. There's no point of sending every single time the 3 bits that over there. One bit is enough, and it carries the same information. Whereas if they are coming is encoding with 3 bits, where then if you have 0 with a single bit flipped, it still probably won't be misinterpreted. So we get the same error correction capability in that sense, while transmitting less bits. So if you think about it, if the probability they are not coming is, let's say, 90%, right? And then again, sorry, going back to the dual binary coding here. So again, we go with the equal probability that they're coming is simply 1, 1, and they're not coming is 0, 0. And we spoke earlier on that that we have that 1, 0 and 0, 1 are out of the dictionary, and that this indicates error detection but not error correction, right? And we did this by assuming equal probability of the 2 events, right? However, if the probability of they are not coming is 90%, and we receive the symbol which is 1, 0, right? So this basically means that if the probability of one event is 90%, this event is more likely, right? And this, in a way, changes our interpretation of the sequence, in the sense that if we have, 1, 0, it is actually more likely to be the more common event with single bit flip than the less common event also with single bit flip, right? It just comes from the statistics. So even though the dual binary code was not really designed for error correction, if we can get some data about the probability of occurrence of the event of the symbol in the alphabet, we still might use that to help with the interpretation. Are there any questions here? Okay. Yeah, and this is actually what sorry, this is actually the slides I wanted to show later on. So on top of that, what we can also do is we can use this variable length code, right? And in that case, you can see that we keep this probability of 0.9 that they are not coming. And here we assign the 3 ones to they are coming and single 0 to them not coming. And on average, of course, 90% of time, you will have transmitted single bit, which is just 0, and only once in 10 time slots, let's call it this way, you would have triple ones. So overall, in average, statistically, over 10 time slots, you would set only 12 bits, right? Because statistically, 9 bits, nine code words for single zero for not coming, and only one will be triple ones for they are coming, right? So you can, with that, you can actually argue that it's much better than just assigning same length of the code words for each symbol, right? In which case you would be transmitting over triple the amount of information, right? Because if both code words are the same length, assuming even 2 bits in code words, that would require, of course, 20 bits per 10 time instances, right? Whereas here you can do equally well with 2, right? And that's also the example when the entropy and information here is of great help, especially with the variable code length, right? And so again, hopefully this is clear. Okay, so basically the message is that in general terms, you can be much more efficient in transmitting your data, in transmitting information, when you can tell a little bit about the entropy and the probability distribution of your symbols, right? And as we saw earlier, actually, human speech and languages, any languages, they are not, they don't have uniform distribution. So they have like some structure, and you can describe them in probabilistic sense, which is actually a good news, because that actually means you can compress quite a lot of information this way. Okay. Now, just like a notation, because I also mentioned that the redundancy is addition of certain certain bits, and so over here we have the 2 messages that we involved, and the information is either 0 or 1, and those are our code words. So they all have 5 bits. All have redundancy in a way of 5 additional bits per 1 bit of communication. However, only one of those codes is actually useful, and the 2 others are pretty much useless. So can you see which one? I propose I will do the chat message with if you can write if you can actually write or like so the 3 options are n repetitions, n-1 added zeros, and n-1 added 1, right? So again, all the 3 codes seemingly got the same amount of redundancy. Which one do you think is the best, or the best? I mean, the only one that actually works and does the job. So you can click like next to your preferred option. Well, like or any symbol, doesn't really matter. Okay. Right. And basically, well, I think most of you got the correct answer. So, or at least most of you participated. At least, so basically, only the n repetition really allows us to do the error correction, right? Why? Because in both this case, the last 4 bits are always the same. All right. So in general, if we got this bit flipped from 0 to 1, it it doesn't really bring us the information, because it could be equally well, either of the two. Or in that sense, here we are still relying on the single bit. So if this one is flipped to 0, the remainder of code is unaffected, because this is like simple addition. I mean, the situation would be different if it would be parity check or anything like that. But just simple addition of zeros is not helping, even though it still adds some redundancy and some information, right? So this is also something that is worth noticing, that you don't want to put any bits. You really want to design your redundancy so that it can help you with the certain type of errors that you're expecting. Okay, and it also highlights one more thing, that what we spoke earlier about the Shannon-Hartree theorem and the entropy. This is just the theoretical limits. Okay, so it's a mathematical calculation which tells you what is possible. However, so far we don't know how to get it, because all that Shannon wrote in that context is, okay, we assuming you have a perfect coding, it is possible. Anyway, it's mathematically proven that it is possible, but how to get there, this is a totally different story. Right, so it's a little bit like a joke with a mathematician in a burning hotel room who says, oh, I see a fire extinguisher, there exists a solution of my problem, and just goes to sleep without using the extinguisher. Okay. So just looking now into the structure of Polish language. Again, this is just I use it here as an intuitive example, but obviously the applications are much broader and not limited to linguistics, right? So okay, so basically any language is a variable length code, and well, Polish alphabet has 32 letters. So if you would like to totally remove redundancy out of Polish language, what you can do, there's of course 32 single letter words, right? There are 32 to the power 2 of 2-letter words, and so on and so forth, right? So this is in general the possible number of 4-letter words. Now, the mainstream version of Polish language is estimated to have up to 10,000 words, basically. All right, even assuming that does not account for declination and conjugation, but still, we could assume that 3 letters, well, 4 again, if you consider declination, should really cover all of Polish alphabet, right? So whatever you want to say in Polish, right, it will be just a combination of 4 different letters taken out of this alphabet. And that's from the information you're pointing to, that's possible, right? I mean, we got 10,000 words, we got certain amounts of letters. That should work. I mean, if you ever played Scrabble, imagine how actually easy game would that be, right? You just put any word and that's it. So, sorry, any letter and that's it. However, why we use long words? And obviously this is oversimplification, because there are also historical and phonetical arguments embedded into language. However, if we have our 4-letter imaginary Polish language, right? And let's assume the words NWJK means chrząszcz, which is Polish for beetle, and MWZK, it's a Polish for trzcina, which is basically a plant that is on the lake, right? And what's happening here? Well, if you don't have any noise, that works perfectly fine, right? However, okay, apart of course from the obvious phonetical problems. However, it's very easy to make a mistake if the signal to noise ratio is low. So for example, if you're at a party, at a loud environment, everybody is speaking, it is very easy to confuse N with M, right? So at the end of the day, the four-letter language would be perfect in the perfect world with no noise. However, as soon as you're trying to use it to communicate information over real channel, you would have so many mistakes that it will prevent your communication, right? So at the end of the day, with language, you want to add redundancy, right? And basically, the conclusion is actually that most of the languages, again, Polish, English, whatever, they have some, error correcting codes embedded, right? Well, it still sometimes may happen that you hear a different word than the person you're talking to intended to tell you. However, this is quite rare, and if you embed the broader context, all the issues, so we can say that actually languages are quite a good, have some quite good error correction embedded. Right, so again, this is just a reminder of how to calculate entropy. Right, so in terms of source coding here, so this is again the example of the other side that that we want to do. So so we just jump from the, so the previous case that we discussed was channel coding, when again we engineer and add some information into our code to to provide error detection, error correction thing. But as we learned on, it has to be like a very specific bits, very specific redundancy, like not any bits won't do the job. So typically before doing this channel coding, we prefer to do source coding, in the sense that to stream or narrow down our information to the bare minimum, so that once we add the additional bits that we need for error detection, it shouldn't be too large, right? And if you think about it again, the gender information in ASCII code, so again using this natural language, requires basically 6 bytes for female and 4 bytes for male, right? So that's okay. 6 bytes might not seem, of course, as a lot, but it's still much more than needed, right? And because the real information that's there is just a single bit, right? So there is we can encode female as 0, and we can encode male as 1, right? This is also something that is encoded in the Polish PESEL number, which we talked earlier, in the form of the second last digit, right? So basically the odd number means female, and even numbers mean male, which basically, thinking that over from 0 to 9, you got 5 even, 5 odd. This is pretty much equivalent of using, single bit to encode that information, right? Okay, so the question is, what is the optimum source coding? In other way, the optimum number of bits to encode an event without using too many letters, right? So again, this is something that we actually did here with our PESEL code, because we squeezed these 6 and 4 bytes into one, and approximately the probability of the ratio of male and females is more or less 50-50. I mean, it's not well, it's close enough to 50-50, right? So basically over here, assigning 0 and 1 bit to each of those value makes sense, simply because the probabilities are more or less equal, right? However, how to do it more systematically? So The optimum number of bits to encode an event with the probability p can be calculated using the logarithm to 1 over probability, okay? So this is again goes back to the principle I referred to at the very beginning of the information theory, right? So that basically means that so the idea here is that the more probable values should have shorter sequence, right? So if you think about it, for example, if you put probability p of being 1, so you are certain of your information. Well, this gives you logarithm based 2 out of 1, which is how much or how many bits? What do you think? Or I'm assuming you're familiar with how logarithms work. So again, what is in your probability? If your probability is 1, right? What will be logarithm base 2 out of 1?
0?
Exactly, right? And why is it 0? Where basically, if you're certain about something, the value of that event is simply 0. I mean, there's no point of transmitting that event really. I mean, there is no point of stating the obvious, right? So in that case, again, the information content will be 0. Right. So okay, and then of course, as your probability decreases, right, then you should assign longer code to your sequence. So in general, right. So in general, this makes quite an intuitive sense if you think about it, or also in terms of the compression, because that actually means that the more common symbols will have like 1 or 2 bits. It will make your message shorter, right? Whereas if something will occur only once per 100 time slots, you can allow that to have very long sequence, very long code word, simply because this code word won't pop up very often into your system, right? So you can afford to sacrifice and have this long code word for something that is not very likely because it won't happen very often, whereas something what you expect on the daily basis should be relatively short, right? Because you will see that probably every second or every third time slot, right? And how to precisely calculate this optimum length is given by this equation. Okay. Now, again, this is as I mentioned, theoretical construct, and the problem, of course, is that we got this theoretical limit, but it doesn't tell us how to do things, right? Partially because, as you can see here, you can get you're not guaranteed that you will get integers as a solution, right? And obviously, it's a bit awkward, to have a code word which has, let's say, one at the beginning and 2/3 of 0 as the second bit. I mean, you need to have integer number of symbols in your code words. And secondly, of course, you want to assign code words so that they don't repeat, right? So for example, you cannot have 2 different symbols or 2 different code words where code word number 1 is simply single 1 and the code word number 2 is double 1, right? This is not going to work simply because when you receive 2 ones, with this coding, you're never really sure whether you mean the symbol number 2 or 2 consecutive occurrences of symbol number 1, right? So your code is ambiguous. It won't work. So there's a bit of a problem. Anyway, this is some example so considering the Bernoulli process, right, which is quite easy because there are just 2 symbols, right? So what if the probability of tails is, let's say, 0.25? What would be actually the optimum, how many bits should encode such a message?
2.
Exactly, right? Because 1 over logarithm 2 out of 4. This is so you want the 2 bits out of for that message. Whereas in reverse, you might have actually less than 1 bit for if you put the probability of 0.75, right? So 1 over that. So this is a little bit problematic, as I mentioned, because you cannot assign non-integer number of bits. And okay, anyway, the solution came sometimes later by a guy named Huffman. Hope that's the proper pronunciation. Who apparently was a graduate student at MIT together with Shannon, and surprisingly, he actually managed to solve the problem on which Shannon and his fellow professors were working on for the last 10 or even more years and couldn't find a solution. Right. So actually, Huffman proposed a system of creating a variable length code that is the closest, as closest as possible to the optimum coding. So let's assume we have a simplified alphabet with just A up to H. This is out of convenience, with these probabilities, 0.4, 0.3, 0.16, and so on and so forth. And first of all, we calculate the entropy based on the equation that you saw earlier on. So overall, the entropy of this alphabet is 2.13 bits per event, right? So in theory, the average code length over certain duration of the time, of course, so using being calculated stochastically, well, it shouldn't be actually longer than 3 bits. That's it should be actually as possible, as 2.13, 2.2, 2.3, somewhere around that, right? And of course, we got 1, 2, 3, 4, 8 different numbers. So again, assuming the trivial coding of just using 0 and 1s, and for equal probability, you would need at least 3 bits to encode these systems, right? Because 8 different symbols in a binary that requires 3 bits. However, knowing the probabilities of occurrence, we can actually do much better than that. And so I will explain why. So first of all, we sort the events from least probable to the most probable, which is over here, right? You get the probabilities from left to right. And then we build a tree by combining together in single branch 2 letters that has the smallest probability of occurrence. Right, so we go here, we join H with 0.008 and G with 0.1 probability. And now they are joined into a single node HG with the probabilities of the 2 that is added. So in that case, it's 0.018, right? And that's our first step. Then in the second step, well, we do the same, but with the joint probabilities, right? So again, we sort them from least to the most probable. So F, then HG, which is combined 0.18, E, D, C, B, A, and we simply repeat. So we again take the two probabilities that are the least, two nodes that have the least probability. So in that case, it would be F and HG, and again we combine them together. And so on and so forth until we have like a full binary tree with all branches connected based on this rule. Okay, so it should look more or less like that, right? So at the end we had this HG that I mentioned. They join in a single probability. Then the two probabilities of HG and F are the least probable. So we get the node FHG. Then it turns out nodes FHG and node E are the two least probable. So we join into EFGH, and so until we have the node with the probability 1 with full set of the alphabet. And then what we do, well, it's a binary tree by definition because we take two probabilities. So we combine each of the edges of the tree as either 0 or 1. For practical purpose, it doesn't really matter which one is which one. The convention, just not to get confused, is to keep, the right one here will be always 1, the left one 0, but frankly, it's just a convention. It doesn't really matter, right? And then once you got the tree with each node numbered as 0 and 1, you simply assign the code based on based on the sequence of ones and zeros that it will take you to get from the root of your tree to the letter you want to encode. So for example, if we want to encode letter C, well, it will be seen as 1, 0, 1. Or equally well, you can go the other way, right? So you go for C, and this is 1, 0, 1. Then if you want to code, let's say H, you go 1, 0, 0, 0, 0, 1, 0, which is the event over here. Okay. Now, bear in mind that this algorithm actually, or this technique of code generation, first of all, it avoids the ambiguity I mentioned earlier, right? So if you just see a bit sequence, there is no problem of misinterpretation in the sense that, okay, assuming of course you start from the beginning, right? But if you see the bit sequence, you never need to think whether this is, symbol X, right, or double the symbol Y, right? Simply because, the tree structure. So if you start with 0, this is A, the most probable letter. If it's 1, when it means it's, further down the tree. And then based on how this extends, you can get every single letter of the alphabet. And secondly is the principle that I outlined earlier on, that the events that are least probable have the longest code, right? Simply because you can afford that. I mean, the code requires quite a lot of bytes being transmitted here, but this is fine because it won't happen very often, right? So overall, it has like a negligible impact of the total amount of communication that you're transmitting. Okay, so is this more or less clear? Or are there any questions? Okay, so in general, because this is, I think the Huffman code and this algorithm is actually something that is, much better if you try to do it by yourself than, me explaining how it works. So my advice would be what I did with the previous years, that simply if you can choose some alphabet or some language, it's pretty much, you can use any language that you can find statistics in the internet, and try to generate the Huffman code for that language. I think that might be a very good exercise, to really make sure you understand how it works, especially very good practice before the exams. And basically what you should came up with is that once you get your Huffman code, you can calculate the average number of bits per symbol, meaning that you have the length of each of the code multiplied by the probability and see what will be the average length of your code using that probability, and then calculate the entropy for the language and compare your code length with the entropy, right? And typically for most languages, both entropy and entropy should be somewhere above 3 bits per symbol. So usually it's ranging between 3.1, 3.2, sometimes 3.3, again, depending on the languages. Although I'm assuming here languages which use Latin alphabet. I'm not convinced. That might be actually different number for non-Latin alphabets, right? And so that's what you expect from the entropy. And typically your average code length, if your Huffman code is correct, should be just slightly, so 0.1 above the entropy, right? And that's when you're right, because your coding reached as close as possible to the theoretical limit given by entropy. It cannot exceed, because if you exceed that limit, if you're below that limit, it means something is wrong, that you're losing information, and that it's not possible to unambiguously recover the information. But of course, it's very unlikely you will exactly reach the entropy level, simply because of the issues I said earlier. And of course, if you're struggling, or if you created the Huffman code, calculated entropy, and you're not sure you did the right thing, well, of course, there's the consultation time, or even you can send me a short email with your calculations, just to either confirm that what you did is correct, or if you struggle, of course, that's where the email and consultation time exists. Okay. So overall, this is the last slide on the Huffman code, and this is just to highlight the benefit of compression with the Huffman code. So over here we have the event from A to H. There's the probability of occurrence P x, and then, well, what we did over here, we have the length of the of code word encoding each of the event, right? And then this is multiplied by sorry, that's something just give me a second. Okay, so yeah, so basically at the end, for using okay, fair enough. So we are assuming here actually that we are transmitting 500 different events, right? So we are trying to transmit 500 different symbols. So it could be like a sentence or anything like that. And of course, using the standard 3 bits, we would use 1,500 bits. However, if you use the coding with the variable length code, on average, we can do with just more than 1,081. bits, which should give, just slightly above 2, which is consistent with the entropy, right? So basically 1081 bits divided by 500 events, that gives you on average 2 and 2.16 bits per symbol. So pretty much close to the entropy we calculated at the beginning, right? So you can see that the saving is real here, right? So we save more than 900 bits really over this 500 symbols being transmitted. Right. So this will conclude our block on the information theory and coding, at least for the time being. So are there any questions regarding to this portion?
I have one general question.
Yeah, go on.
So let's say that we have some system and we want to transmit data, and during transmission we added some redundancy to detect if there was error during transmission. And the receiver needs to be sure that this data is correct. So let's say it also performs checksum to see if this data is correct. And if it's not correct, it sends back information that it needs to be retransmission. And if we were to start decreasing the amount of redundancy in the transmission, we would on the beginning see that bandwidth at bitrate is increasing, but after some point we would start to see that on average it's decreasing because we need to retransmit more and more packages. So is there some way to see that we how much we can remove redundancy before that retransmissions will be, that cost of retransmission will be too big?
Yeah, this is actually a very good question, and basically the answer is typically it really depends on your signal to noise ratio, right? So because the signal to noise ratio, it tells you how probable it is to for certain type of error to occur. So for example, if there's no noise in your system, you might add just a very simple redundancy, because again, if you're flipping, let's say 1 bit over 10 to the power 9, right? Then it's not really a problem. It's not a valid approach to repeat that bit, right? However, once your signal noise increases, then it might be useful to add more redundancy. I don't think there's one answer to your question. Also because it depends a lot on the application, right? I mean, the number would be different for medical devices, right? When, sometimes even a single bit can be problematic, or for example, if you're doing, live streaming and you need low latency, right? Then that will put basically your code into totally different position. So the scheme, you notice this is 100% correct. That's how it works. And also you have to bear in mind, right, that sending this request is also transmission that can be prone to errors. However, I don't think there is one size fits all answer to your question. So it really, I think, depends on firstly on the amount of noise, because that dictates, how likely it is to have errors and bit flips, and then how important is really that information in for your systems, or how critical it is not to have bits flipped in general. Okay.
Okay, thank you.
I hope that's as much as you can say. And yeah, and then if you're actually interested, you could just look into different protocols and different systems, which each will probably use different coding. Okay. So with that, we have still I think 20. Okay, that's so we have 25 minutes left, if I'm not mistaken. Okay, so we'll start now the next block. So now we are trying to we learn the basic theoretical foundations, some theory and so on, but obviously we want to move now towards more practical applications or more practical aspects of the telecommunication systems. And so this will be more like an overview through different ways of telecommunication, and we basically start with some basics on the radio channel. So this again just some background literature that you might like to explore. So basically, we'll try to look in what's called the spectral space, a little bit more about noise and the practical implications, what is interference, compatibility, and also we will talk about the decibel scale. So in general, I'm kind of, the decibel scale is considered more as a repeat, but in general, if you're not yet familiar with the decibel scale, I highly encourage you to get familiar with that and do some random calculations, because especially with radio systems, with telecommunication, it is very commonly used. And as a matter of fact, believe me that even though at the very beginning it might be a steep learning curve, at the end of the day, if you can operate with decibel scale, it actually makes your life easier. Simply because then you can do like a quite complex calculation simply in your head in a matter of seconds. And this is, well, obviously useful not only during the exam when you have a limited time, but later on as well. Okay, so going back to the slide of multiple access, we already know two basic types, that there is a frequency division multiple access at DMA. So this is represented here on the left-hand side, and the time domain, which is TDMA, right? When we allocate users based on the time, and this tells us how many users we can accommodate into a system, given, of course, assuming certain bandwidth and time requirements. However, in practical terms, there is, of course, the third dimension to this, which is space, right? So obviously, if you have two transmitters that are sufficiently apart from each other, well, it is likely they may not interfere with each other, even though they transmit at the same time and same frequency. All right, so this is something. Okay, let's leave it here maybe. Okay, so if you combine bandwidth, space, and time, or BST, this is like something that a spectral space available to the users, right? And basically, prevents other transmitters to use this space in the sense that if you have two signals which are present at the same time, at the same frequency, and at the same spot, the same location, the space dimension, they will just merge, interfere with each other, and of course the effect will be that they become indistinguishable, and you cannot make a distinction between them. Now, there is an asterisk here because hopefully some of you thought, okay, wait a minute, how about CDMA? And of course, you can use CDMA and embed some code into that to make them distinguished. If you thought about that, that's a fair point to you. However, the problem here is, of course, that CDMA is not very efficient, right? Simply because the fact that we need to embed individual code that will reduce our communication throughput for that system. So typically, in most of the systems, telecommunication systems, CDMA is not that common. It's not that commonly used, although some systems are obvious exceptions. Okay. So basically, what we want to do, well, we want to have some radio communication systems in the form of a plan. And you typically would have both transmitters and receivers, which can be described by the location, the frequency over which they operate, and spatial distribution of radiated power. Okay, so the spatial distribution of radiated power is simply given by radiation pattern of antennas. We should talk about that either next week or in 2 weeks' time. Well, then frequency, this is the bandwidth that certain transmitter occupies for a center use, and of course location, that should be quite clear. Okay, and typically when we have two transmitter, each of them will generate signal, which, as we know, decays with the power 2 of the distance. In practical terms, of course, it's not just a smooth decline because of interference of reflected signals and many factors that will be experienced. However, in general, what we can see over here is that we have two interference areas. So within the pink region, this is what's called the useful range. So this is basically when the area within which the transmitter or the principal transmitter, so in this case the transceiver A, gets strong enough signal to communicate with all users allocated here, and all other interferences are negligible, right? So again, we are speaking here about the signal to noise ratio, or more specifically signal to noise and interference ratio. Okay, now, however, there is a region here which is marked here as the red spot, where our transmitter, the power is simply too small to have meaningful communication. However, the signal is still strong enough to generate interference, right? And as you can imagine, this is quite problematic, simply because this small interfering signal will add up to your noise, hence the name signal to noise and interference ratio, and will decrease the quality of communication for neighboring signals, right? So at the end, you have this useful useful area when you can communicate, which is pink. However, wider outside of that would be the red area, where you are not really communicating, but you're just spoiling the fun for others, so to speak, right? So you basically limit the capability to communicate of other systems in your neighborhood, right? This is, again, of course, assumes transmission at the same frequency and same time. Okay, so basically this is something that we talked. So we're assuming here we have an what's called this isotropic antenna, and we have radiated power, which is denoted as PR. And again, we have the same power which starts to propagate within our sphere. And again, assuming the lossless case, this is still the same power PR, which however need to cover larger areas as it moves away from the transmitter. So at the end, if you want to see power density per certain area, we can calculate that as the original radiated power divided by the 4 pi r to the power 2, which is the lower component is simply the equation for the area of a sphere, right? And one maybe comment why we are talking here actually about the power density. So simply because this is something that is the most useful for us, because when we have receiver's antenna, the receiver's antenna typically is put out there to capture incoming radio signal from certain area around it, right? So basically, on the receiver side, the power that will be received at the receiver is simply the power density of a given area multiplied by what is called effective aperture of receiving antenna, right? And then it's simple as that. So each antenna will have, of course, different area. In general terms, the bigger the area of your antenna, the more power it can capture, simply because it can interfere with larger fraction of this power power density here, right? Okay, so anyway, from the point of view of the energy, we have here the two examples. So one, we have like one huge transmitter which covers certain area, right? And then we have multiple smaller transmitters, each covering smaller area by itself. However, overall, from the system point of view, they both allow communication within the same area. And here comes a question to you: if you can figure out what are the pros and cons of both those setups.
So one transmitter probably costs less, but 3 transmitters can, for example, serve more users.
Okay, so yes and yes. So the second argument is actually something more advanced, but that's correct. Yeah, with the first one, obviously, the lower one transmitter in terms of the development cost. So the initial cost you need to put to put the thing there, equipment and so on, is on general lower than 3. Okay, that's true. The argument about serving more users, well, yeah, that's okay. That's also yes, that's true. Assuming, of course, there is no, yes, that's also true. How would it work in terms of power? All right. So which solution would be more efficient in terms of power that you're delivering? Okay, so bear in mind the previous slide that I showed to you, right? That the power density changes with the square root of 2, right? So if we want to cover the same area with one big transmitter or 3 smaller one, where we need to put more power into the system actually.
One big one.
Exactly, right? The big one. And the problem is, of course, that it does not scale linearly, right? So over here, you need actually 9 times higher power, right, to serve 3 times bigger area, right? So in terms of power efficiency, this solution is actually much better, okay? Also, another factor related to that, if you think about the 9 times greater power, right? Over here, you would have stronger power variation in the sense that if you're very close to your antenna, you will have very strong power, which of course decays over the distance. Okay, so from terms of the legal limits, from terms of health and safety standards, that might be a problem, and very often is, right? Because there are certain caps on the amount of power you can transmit from a base station or a transmitter, right? And also not to mention factors such as the cost of electronics. So you mentioned at the very beginning that, of course, building one transmitter is cheaper than building 3, which is of course true. However, because of the power handling capabilities, this transmitter will need to deal with 9 times greater power, right? And that may also drive the cost of the transmitter, higher. So here the cost balance is simply not that obvious, even though probably one transmitter will still be cheaper than 3. However, single transmitter will be more expensive here than single transmitter here, simply because it will be more complicated. It will be more designed to carry higher power levels. Okay. Lastly, some issues which this might be not very obvious, but if you think about the 3 different transmitters here, right? What problem we might experience at the border between the areas covered by each of the 3 transmitters?
Increased interference.
Exactly, right? So we need to come up with something to avoid the interference at the borderline, because if we know that if we use the same frequency, the same and the same time, pretty much users which are here and here, they will experience high interference. So they won't be able actually to have the sufficient quality of service once they reach this area. This is typically actually done simply by using different frequencies between neighboring transmitters. At least that's how the mobile phones are dealing with this issue. Okay, and another possible problem. So, assuming you are mobile communication, right? So again, thinking about your phone. Let's say you are driving your car and you're moving from here, the area covered by one transmitter, to the other. All right, and then if you are transiting from one area to the other, well, it wouldn't be actually a problem if all 3 towers would transmit at the same frequency, but we know usually this is not an option because of the interference. So if you're moving, you also need to have some way of this is called handover, right? So basically, your phone needs to seemingly switch that from between different base stations or between, but base station in that context means also different frequencies, right? Because as we know, each base station will use different set of frequencies here. And of course, you don't want to have a mobile phone which you're calling to, well, whoever you're calling, right? And you say, oh, wait a minute, like I'm moving to a new cell or new area of base station. I will call you back once I catch the next tower. That's obviously not gonna be very liked by your customers there. Okay, so in general, there are certain issues with each of those. So all the points that I mentioned last, it also adds in a way as advantage of this solution, which is simplicity, right? Because here you just put a lot of power and you don't care for anything, right? Whereas here you need some subtle solutions to take care of different things. And if you compare these two setups, you can see that the upper one, this is actually the solution which is very often used for TV and radio broadcasting, right? So basically the classical setup when you have one transmitter, so this is one-way communication, where you simply transmit, signal over large area without really worrying about, covering multiple users that will, call you back. And also because of the simplicity issues, of course, this solution is historically the simplest one, right? So if you think about the radio TV broadcasting, that would be the case that is most commonly used here. Whereas this solution, that's pretty much common setup for most of the mobile phones, right? With all the pros and cons that that we discussed earlier, the capability of course, handling more users in a bidirectional way, or as it is called, duplex, where each user can also transmit and receive, as well also as the power concern, right? Because in the middle of the city, you cannot generate too much powers above certain legal limits. That's not going to happen. And okay, so maybe just telling a little bit about frequency allocation, and I think that will conclude our lecture for today. So yeah, typically this is like a Polish telecommunication institute spectrum allocation. You can always have the United States frequency allocation. So basically this shows spectrum from very low frequencies such as 3 kilohertz up to 300 gigahertz, right? And you can see that typically all the use of spectrum is quite heavily regulated by the government, well, by the government, depending on the responsibility. So this means that typically, like, a spectrum is a very scarce resource because of what we said earlier, that once at a given time and place, you can use spectrum only once, and it makes it's heavily controlled and regulated by the government. So, for example, typically when you have a new mobile operator, or actually it's different stories. Sometimes when you have a new mobile operator, so every now and then the government will announce like a bidding of a certain frequencies. All right, and so typically there will be a public auction where the government says that they will give a right to certain companies of using certain portions of the bandwidth of the spectrum for mobile communication, right? And typically, that's quite a high income for the government, because operators like T-Mobile, like Orange, or whatever there is operating now, they sorry, they actually had to pay quite a lot of money for the government for the right of using that spectrum for the mobile communication. And that license is, of course, covering part of your bill for your phone or any other provider that you're using. And also that also means that the companies, are entitled to using certain fraction of spectrum for the mobile communication, but also that in that case, there are very strict about exceeding that limit, because if you pay a lot of money for the right of using that, you don't want anybody to interfere with your signal or come into your bandwidth. And there are basically a heavy policy and heavy penalties for using that in the spectrum allocated or in the frequencies allocated for mobile communication. On the contrary, of course, you can think about Wi-Fi, right, or certain portion of spectrum which are pretty much open to everybody under certain conditions. So in terms of Wi-Fi, there's simply a maximum effectively isotropic radiated power. So it's power limited, whatever your Wi-Fi router can transmit. And within certain, as long as you satisfy certain conditions, you just set up your router there and ensuring basic compatibility. Of course, the frequency is open to use for everybody. So that's a bit of the legal aspect. And I think I can stop here with our today's lecture. So are there any questions?
Yeah, I have one question about the spectrum for Wi-Fi. It's only that it can be you can radiate more power, or is it you need to use it for Wi-Fi?
As far as I understand, there is basically some basic power. So it's strictly to be super precise. This is not only this is called effective isotropic radiated power. We will talk about that, I think, in 1 or 2 weeks' time. So this is the maximum power, including focusing of your antenna, right? So basically, it's not, strictly speaking, the limit is not on the power you put from your amplifier into antenna, but this is the power that is already there outside of the device in the ether, so to speak. Just the maximum power that is transmitted already by your antenna. And if I remember correct, okay, no, sorry, I will stop here because I don't want to put you in make a mistake. But in general, there is, I think, a limit on the maximum power that can be transmitted. Okay. So for example, the side consequence is that because it's not a transmitted power, if you use bigger antenna with more directivity, technically you might be violating the legal limitation on your Wi-Fi signal, even though the power that gets out of your amplifier is the same, simply because your antenna has higher gain and more focusing. But again, about antenna and focusing gain or antenna gain, we will talk in 2 weeks from now. But yeah, but basically there is an upper limit of the power that can get out of your Wi-Fi router.
Okay.
Any more questions? Right. So, okay. Okay. So I think with that in mind, well, thank you for attending the lecture, and I wish you a nice weekend. And once again, there is the consultation time at 12, or if you have any issues, you can always send me an email and we can agree for a talk on at any day. And also, I do encourage you to try your take on the Huffman code and try to create one just by yourself. That's not only with respect to Huffman coding as such, but also that entropy, to get familiarized with the concept of entropy. Okay, so with that, thank you very much, and I see you next week.
Thank you. Bye.
Bye. Thank you.
Thank you. Goodbye.